and good evening or good morning, good afternoon, everybody, wherever you are on this planet. Today I'm going to talk about demand side efficiency and the importance of downstream measurements. So let's get started. So, um, so why would you monitor compressed air? Well, in a lot of factories, it's a considerable part of the energy consumption. Sometimes 10, sometimes even 30% of the utility bill. It's very expensive. The efficiency of a compressed air system is typically causing that it's about 8 to 10 times more expensive compared to the equivalent cost of electricity if you would use an electric tool, for example. It's misunderstood and it holds a high potential for energy savings. And of course, it's vital for a lot of machines and production processes. So you cannot live without it. So looking at energy savings in compressed air systems and increasing the efficiency, we believe that you should do this not only at the supply side, but also at the demand side. It really goes hand in hand, because if you walk around, for example, in a plant, which I did quite a few times with our partners and customers, you will see things like little oil spillage on the floor. And if you talk to customers, like the operators of the machines, they will tell you like, well, this machine sometimes fails, and then we have a production stop. And so it already gives you a lot of information, the demand side, on basically how well the whole compressed air system is performing. And you will also find out that when you're starting to fix things in the demand side, it will affect also the supply side. So the compressors start to run differently. The controls sometimes need to be adapted, and even sometimes you can just turn off a compressor when you basically fixed enough leaks. Sometimes you can turn the compressor off. And a nice example of this is this project that we were involved in a textile plant somewhere in the Far East, where they had 48 loom machines, basically producing textile fabrics, as you can see on the picture. And they invested in a few flow meters, basically to see which machine was consuming how much air, and they found that there was a lot of leakage and a lot of waste. And simply by fixing those leaks, they were able to optimize the production, and even better, they were able to add 4 more weaving machines without having to invest in additional compressors. So this was really a nice example where optimizing the demand side basically gave a lot of benefits for them, and also on the long run, now they're monitoring it permanently, so they can always keep track of those leaks. When they happen again, they can fix it right away. Now, to do this, basically you need a flow meter to go down into your plant and measure flow, pressure, and temperature. The best thing is to have a flow meter which measures all 3 in one, because then you have everything straight, in one Excel sheet or in one logging file, and you can also see the correlation between those two, or those 3 even. So, and a lot of times you will see that if the demand is excessive, then you will also see a pressure loss, or a pressure drop in your system. You will also sometimes find out when there is a temperature change, there's also a flow change. So it really helps you to get down to the root cause of the problem. And you can also try to tweak and tune machines and see if it can operate at a lower pressure. So that's also a nice thing to have these all in one instrument. But there can be other reasons also, of course, to measure flow. You can use it as a point of use measurement device to allocate cost to specific machines. You can measure the pressure throughout the entire network. So, if you have each machine with a flow meter, you can see basically the gradient of pressure from the start of the factory to the very end of the factory. And you can benchmark machines. You can look at a new machine and an older machine, or sometimes even you find that depending on the product that is produced on a specific production center, it uses less or more air, or maybe the operator changed a few things or changed some components, and then you say, hey, but this machine should be identical to the other one, but it's using less. So what can we learn from this? Leakage management. A flow meter is definitely the quickest way to find leaks instantaneously if you compare it, for example, to pressure decay. It goes, of course, hand in hand with an ultrasound leak detector to find where the leak is, but the flow meter gives you already a direct signal that there is a leak and that you should do something about it. And creating awareness. So a flow meter can also help to create awareness for the operator. So it knows, the operator knows that, hey, if I tweak this dial a little bit, I'm using less air. And you can even put a currency on it that you say, hey, if you turn this down, it saves you so many euros or dollars on an annual basis. And you can, of course, also create incentives to reward people for reducing those costs. An important thing that sometimes is not really well, let's say, specified with machines is duty cycle and the effect of the duty cycle of your machine and how it influences basically the average flow. And as you can see here in this these example graphs, if you change the duty cycle, say the machine is running faster, or even when it's producing different products, you can also see that the flow is basically intermittent and changing, resulting in a higher or in a lower flow. And I've also seen machines where this was in a can factory where there was no product running through the machine, and then the flow would go to an instantaneously high value, which was causing other machines to stop because it causes a pressure loss, a very big pressure drop in the system. So be aware of these duty cycles and what they can do basically with flow and with pressure. And sometimes it's easy to resolve these issues by placing a receiver tank near the machine that can basically equalize out this pattern, and then it creates basically a more steady pressure and also a lower average pressure in the entire network, which eventually will save you money. What you also can do is combine flow for compressed air and vacuum together with kW, and also with a counter that counts basically the number of widgets you are producing. And in this way, similar to a compressor efficiency graph, you can create a machine sort of efficiency graph. And you can sometimes find out in this way that the machine has a certain sweet spot where it basically produces the maximum amount of widget at the best efficiency. And if you run it too fast, then there might be a lower efficiency number. It can also help to test new machines or to find differences between somewhat identical production centers. So this is a great way basically also for maintenance management to see if there's something is going a little bit out of control. Then you know that you have to do something like maintain a certain component of the machine or change the setting. Dew point can also be measured not only at the supply side but also at the demand side. Obviously, when you mount it, in most of the cases, you will mount a dew point sensor directly straight after the dryer. And if you combine that with a flow meter, in that way you can of course see the relation between the demand and the dew point, which is very helpful to prevent oversized dryers. But you can also mount a dew point sensor downstream. This would be sort of watchdog, or say a warning that something is going wrong with the dew point, and that could be helpful, for example, to prevent production losses. You can also, if you find differences between the dew point you're measuring downstream and the dew point at the dryer, and if there's a huge difference, then it could be an indication of leaks, because if there are air leaks, water can intrude into the system through those leaks, and it will affect the dew point downstream. So in that way, it's also a sort of leakage indicator. This is a nice example of a project that we were involved in a cacao factory in Europe. This was typical, an example of optimization both at the supply side and the demand side, where at the supply side, by implementing a modern control system and changing a few things in the compressor configuration, they were able to increase the efficiency. But at the demand side, they found huge leakages, and these were fixed and resulting in a savings potential of even higher than $100,000 per year. But not only that, they were also able to increase the production capacity of one machine, because the cycle time of that machine opening, closing to crunch those cocoa beans, the cycle time was improved by fixing the leaks. So they could basically increase the whole production on that specific machine, which was a quite a big piece of capital investment if they would have to buy another one. So this is also a very nice example of that demand side optimization and supply side optimization can go hand in hand. Dust collectors are also famous pieces of equipment there, or maybe infamous, I don't know, but sometimes there's a lot of leakage in those dust filter shakers. They use pulses of compressed air, and the pulses are generated typically by membrane valves. And yeah, guess what? These things tend to break after some years, and nobody wants to climb up that ladder. So yeah, it's always a sort of neglected thing in the factory, and people start to run at it maybe when it's already too late. And in this case, also in the steel plant, they found out that the actual air consumption was way higher than they would expect. Also, the filters were not cleaning properly anymore because a lot of the valves were broken. And well, thanks to a flow meter and some other equipment mounted on this on these filter baghouses, they were able to save between 20 and 30,000 US dollars per year, and they also could optimize the maintenance interval for these filters. Next slide shows an example graph of how it looks. So first of all, before repairs, you see that the flow is intermittent, sometimes high, but it never really goes to zero, and it should go to zero if all those valves were working properly. And you see after some repairs already the flow starts to decrease, and you see even that the flow sometimes goes to zero. So that is a good indicator that they fixed it. So you see first they fixed half of it, and then here they fix everything, and the flow is at a lower level. So there was a very nice example of also demand side optimization and maintenance management. Let's go to the next slide. Yeah, the air nozzles. It was a little bit slow. So this guy from Italy, Mr. Venturi, somewhere in the 1700s, I have to read it up. It's 1797. He invented this Venturi tube. So it's a long time ago, but we can still be very thankful that he did, because these Venturi tubes are now used, or the same principle is used in air nozzles. And those air amplifiers, they amplify basically the air. By using a little bit of compressed air, they drag along also the ambient air. And the nice thing about this is that it can result in 35%, sometimes even higher, compressed air savings. So where can you use these? Cooling, blowing, transport, sometimes also for vacuum. So and we had a case in Czech Republic. I will show that in a minute. First of all, how do you do this? You can use a flow meter to basically see the difference between the existing situation and the new situation. And this similar flow meter like this was used by one of our partners in Czech Republic, where they had these open blow pipes. This is a picture of them. You see it's a very nice piece of artwork almost. 3 pipes here, and 2 are closed with some kind of nuts. And these were used to blow off the chips from wheel rims before they would go to the spray paint department. So these are automotive wheel rim cleaning cabinets. Now, this was not looking very nice, so they thought, okay, let's talk to a local supplier of nozzles. And let's see what they can bring. So here you see this graph where the airflow with a nozzle is basically almost cut in half. So they were able to save, in this case, 50% of the air consumption. And I mean, it's not a big amount. It's only like 9K a year, but it was also only an investment of like 1.5 or 2K for all those machines. So it's still a very nice example. Yeah, how you can optimize demand side and save already some money and have a really quick return on your investment. Nozzle manufacturers, they have also these tables you can review on websites of various. This is one from Sylvant, and you see that depending a little bit on the size, and compare that then to an open pipe, you can save between 20 and say over 50% sometimes. So it's really worth the investment and the money. I would recommend always to involve people from production when you do this, yeah, because you have to, of course, also look at the product quality, and sometimes you have to talk to some engineers on how to combine these nozzles to get similar results for a specific process. So this concludes my part. Demand side savings, they go really hand in hand with optimizing the supply side. And you should always look at it as a sort of holistic approach. Demand side monitoring also leads to improved production processes and to increased production capacity without basically spending a single penny on new equipment. There's a lot of low-hanging fruit. The nozzles is an example. Lowering the pressure, sometimes placing a small receiver tank near a machine to basically smoothen out the pressure that supplies that machine. And you can start really simple. Just take a flow meter, preferably ours, but you can also use another brand. Basically, a 1-inch inline meter with a data logger can already be very helpful to find those low-hanging fruit, apples or whatever fruit you like, and it will really open your eyes and open the door towards more savings in your plant.